We have some examples for section 8.2, claims about a population proportion. Follow me over to my other screen. Don't get lost. All right. Hypothesis test for proportions. I'm going to remind people there are two approaches. There is the traditional method, also called the critical value method. And I'm going to use it just once. I like it because it is so visual. It really gives people a good idea what happens with a test of hypothesis. After we've worked with the traditional method just once, we're going to go ahead and do all our other examples with the p-value method. Forevermore. Anytime statistical results are conveyed, they're conveyed via some sort of p-value. So it's really the way things are done. Tools. Well, I'm going to use the traditional method, and you're going to see me do it the first time anyway. I'm going to need a critical value, which means inverse normal 83, or perhaps the inverse norm program if you've lost access to your software that I downloaded. In addition to that, we want the one prop z test. Now, that'll give me the test statistic, which I'll plot relative to the rejection region. If I'm working with the p-value method, it's really just the one prop z test. That one prop z test is going to give me the test statistic and the p-value. So at the end of the day, it's really this guy here that we like, the p-value method, and I'll use the one prop z test. But you're going to see me do the traditional method first, and then we'll take a look at the p-value method. All right, so let's take a look at an example. More than 20% of voters have used a mail-in ballot. We're going to test the claim at the 5% level of significance. So we have a claim, more than 20% of voters. I need some sort of numeric representation. P is greater than 20%. And I can see by that particular statement, the lack of equality in that claim means I'm looking at the alternative hypothesis. We're going to test the claim at the 5% level of significance. That is our alpha. So our alpha for this is 0.05, and we'll use that when we set our critical values and rejection regions. I've also got the raw data here. And the question really is, is my p hat far from the null hypothesis? If it is, then I'm going to reject the null hypothesis and go with the alternative. So here we go. There is the claim, P equals 20%. The alternative, P is greater than 20%. And this is my claim. I will keep track of that. I will address the initial claim, there it is, at the end of the problem. Now, the traditional method means I want to draw a distribution. We use the z distribution. There's the 0 there. It is a right-tailed test, so my critical value is there on the right, and my rejection region is in there. Now, once I calculate my test statistic and plot that, if it plots out here, I'll go with the alternative. If it plots in here, I'll stick with the null hypothesis. So I need my critical value. This is where I'm going to use my program. I'll use the inverse normal program. We have a right tail test. All of alpha 0.05 is there on the right tail, and I get a critical value of 1.645. All right. Put him outside for a moment. He'll come right back. So now I need to calculate the test statistic. So follow me. Stat over to test. One prop z test. The null hypothesis 0.20. If you use 20, you'll get an error message. The x 27, the n 100. Now I've got to adjust my alternative hypothesis, and you'll note that we've got a place for the null and a place for the alternative hypothesis within the test tool. It's an important component here. So I've selected the right tail test. It should match up. Now I can hit calculate, and I'll get my test statistic, 1.75. So that test statistic, 1.75, needs to be plotted relative to this scale here. I have a 1.645 for my critical value. 1.75 is a larger value. So when I plot that guy there, he lands in the rejection region. This tells me what I need to know. So I will reject the null hypothesis. Now that wraps up the statistical portion of the test, but I really need to address the initial claim. The data. Now before I go ahead, remember what this means here. To reject the null hypothesis means you're going to go with the alternative hypothesis. So the data support the alternative hypothesis, p is greater than 20%, at alpha equals 5% or 0.05. So any good statement here has a couple of things. Number one, we have whether the data support or don't support the initial claim. I state the initial claim for clarity, and because things really depend on the level of significance, I always mention alpha. So traditional method, 1, 2, 3, 4, 5 steps. Now, that's the traditional method. The next example, we'll take a look at the p-value method and compare. All right, for this particular one, we're going to test the claim that 30% of drivers would buy a self-driving car. When I translate that statement, p equals 30%. And I note that that particular claim contains equality. So my claim comes to me, my initial claim comes to me as the null hypothesis. We have a level of significance, alpha equals 0.05. And we have data. Now, once I run through the test, I'm going to redo this problem with an alpha of 0.01. And we're going to go ahead and compare. Now, step number 1, H0. P equals 30%. The alternative, P is not equal to 30%. So there is my statement. We have the claim there. Now, my calculator comes out to play, and I use the one prop z test. My null hypothesis, 0.30, 30%. How many X's? 227 people said they would buy a car that would drive itself. 859 people responded altogether. You'll have to adjust your alternative hypothesis to pick up the two-tailed test, and then we can calculate. Now, I'm not after the z-score here, I'm after the number right below it. That's the p-value. I'm going to round it to 3 significant digits because it is a probability. So I'm looking at p equals capital P 0.0223. Now, that's the number I compare to the alpha. If the p-value is less than the alpha, we reject the null hypothesis. And 0.0223 is less than 0.05. So we reject the null hypothesis. Now, I need to address the original claim. I'll note that the original claim is indeed the null hypothesis. So if we've rejected the null hypothesis, that means I'm going to keep the alternative. So that means that the data do not support P equals 30% at alpha equals 0.05. So there's the 1, 2, 3, 4, and 5 steps of the p-value method. Now, the nice thing about the p-value method is once you develop that p number, the p-value, you can use it again and again. So when I'm asked to redo the problem at the alpha equals 0.01, the only thing that will really change is this number here. That's the only thing that changes. So to redo the test, that doesn't change. The data is the same. That doesn't change. The only thing that changes is that number right there, the p-value, the alpha. Now, when I make my comparison here, because my alpha is so much smaller, my p-value is now larger than the alpha. So now we fail to reject the null hypothesis. And that was my initial claim. So that means I am going to keep the null hypothesis. Now, when my data drops, or my alpha drops to the 0.01 level, that changes the way I state the outcome. So in this case, the data do support P equals 30% at alpha equals 0.01. So you'll notice that we switched from do not support at the alpha equals 0.05 level to the do support here at the alpha equals 0.01 level. At the end of the day, smaller alpha means it's harder to reject the null hypothesis. Thank you so much. Goodbye for now.